Hello students, welcome to lecture 3.3, the biosphere and flow of energy. Before we get started on the lecture, I just want to point out a couple of handouts. Um, this handout right here, this is the notes handout that goes with this lecture. This can be found in under the notes presentation and notes guides where you found the link to watch this video. So go ahead and have, if you can have a split screens, have this open on one screen. Otherwise, you could be watching the video on your phone and have this open on your Chromebook, your laptop, your desktop, so you could fill this out as you watch it. Again, this handout is found in the notes presentation and handouts folder under Chapter 3.4 in Schoology. Okay, so we spent the first several weeks covering chapters 7, 8, and 9, and a major theme, particularly in chapters 8 and 9, is the flow of energy. And we looked at two chemical reactions. We looked at the chemical reaction of photosynthesis and how the energy flows from the sunlight and into living systems through the process of photosynthesis, and that light gets trapped into the chemical bonds of glucose. And we also looked at how energy flows through the system from cellular respiration, the chemical reaction of cellular respiration. So that glucose, that has a high energy molecule, then gets converted into a second high energy molecule, ATP. So really all of chapter 8 and all of chapter 9 was about the flow of energy, but we looked at that concept at the biochemical level. We looked at the actual chemical reactions that flow that energy and the structures within the cells and within the plants that where those chemical reactions take place. Chapter 3, a major theme, is also the flow of energy. But this time we're not looking at the molecular level or the microscopic level, but we're looking at how energy flows through systems, meaning from individual to individual to individual, and through entire ecosystems. So the theme is the same, flow of energy, but now we're looking at it at a macro scale, not a micro scale. All right, so there's our big idea. The Earth's living and non-living systems parts constantly interact and shape organisms' environments and affect their survival. All right, so energy flow in ecosystems. Energy flows in a one-way stream. This is a major theme in this chapter. The two major themes in chapter 3 can be summed up in two phrases. Energy flows one way, but the matter, the stuff that makes up those systems, gets recycled. So energy flows one way, matter recycles. So the energy starts with the sun, flows through the producers, and then from the producers it goes into the various levels of consumers. But it's a one-way stream. The energy at your top level predator, say a grizzly bear or a great white shark or some top level predator, that energy never recycles back into the producers. The energy just flows in a one-way stream. All right, so energy flows in a one-way stream in an ecosystem. A food chain is a series of steps in which organisms transfer energy by eating and being eaten. Now, you've known about food chains since like third grade. The concept of a food chain is not new. However, we're not going to think about it in terms of what creature eats what creature. We're really going to think about it in terms of energy flow. What organism is being consumed and which organism is doing the consuming is really immaterial. That's secondary to the concept of the idea that ultimately what it's about the flow of energy, the movement of energy from one living thing to a next. And note the direction of these arrows. So here we have our producers, our algae, our primary producers, and that's consumed by the flagfish. The flagfish is consumed by the largemouth bass, which is eaten by the anhinga, which is eaten by the alligator. Now, these arrows do not indicate what's eating what, right? The algae is not eating the fish. The arrows indicate which way the energy flows. So the energy that starts in the sun and gets captured in these producers by the process of photosynthesis then flows through these systems through various levels of consumption. So the arrows indicate the direction that the energy is moving. The energy is moving from the algae into the fish, from this fish into this fish, through the bird, and then finally up to the alligator. Food web, again, not a new concept to you, but the idea of energy flowing through a system, that's how we want to think about it. So that's sort of that next level of complexity. Food web is just a network of feeding interactions. We just have the little asterisk there. Don't forget the decomposers and the detritivores. So these are the detritivores are things that consume dead and decaying matter, like an earthworm. Again, if you find that I'm going too fast, just take a second and pause it to fill in the notes assignment. Now, this is a really simple food web. It just has 2, 4, 6, 8, 10, 12, a dozen organisms on it. Real food webs in real life are incredibly complex because you have so many different kinds of consumers in each level of the ecosystem preying upon each other. So this is just a really simplified version. And again, pay careful attention. Look at which way the arrows move. The arrows indicate the flow of the energy. And notice how all the arrows originally start from a producer. Arrows flow out of this producer. Arrows flow out of this producer. Yes, arrows flow also out of some of the predators, or some of the lower level prey, but that just means that this grasshopper is consumed by this bird, and this bird is then consumed by this owl. The arrows indicate the direction that the energy moves. Now, the difficulty with the complexity of food webs is predictions can be quite difficult, especially when you have incredible disruption to these systems. The most prevalent example right now is climate change, and how climate change is disrupting these ecosystems. And what we see is climates being driven to extremes. Cold climates are becoming colder, actually. Hot climates are becoming hotter. Wet climates are becoming wetter. Dry climates are becoming drier. Now, that's just a generalized statement. There are exceptions to that rule, of course. The point is that these systems are so incredibly complex. These systems are so complex, and there's so many variables that go into determining the outcome of the interactions of these living things, that predictions, under the best of circumstances, can be very challenging, let alone when you talk about massive disruption to the system, like, for example, oil spills. Now, again, here's just a simplified food web of an ocean ecosystem. It's not anything that you need to memorize, but what happens to the complexity, with all this complexity here, what happens to this system when we introduce oil into the system? When I was your age, in 1989, up to that point, it had been the worst environmental accident in the United States. The Exxon Valdez ran aground in Prince William Sound in Alaska, spilling millions upon millions of barrels of oil into the water and on the beach. And you can still go there today. So 30 plus years later, you could go to the beaches in Prince William Sound and with a shovel, and you only have to go down about 3 feet or so, and you can still find oil in the sand. The worst one in the United States since then was the Deepwater Horizon that erupted in the Gulf of Mexico in 2010. Now, again, that's just 2 examples, and it takes oftentimes decades to tease out how that disturbance is going to affect and shift ecosystems, just because the relationships are so complicated. And just a couple of clips from some examples. All right, so now here's the main big idea from this section. this idea of flow of energy and trophic levels and ecological pyramids. Please make sure you're paying careful attention, taking careful notes in this section. All right, so a trophic level is just simply a step in a food chain. So a 4-level food chain: producer, first level consumer, second level consumer, third level consumer. That's got 4 steps in that food chain. That has 4 trophic levels. A typical food chain might have 4 or 5 levels in it. Some more, some less. So it's really just a step in a food chain. All food chains start with producers. They start with some animal, some plant mostly, or some organism that can photosynthesize. There are some exceptions. There are some bacteria way down in the bottom of the ocean that can chemosynthesize. They can actually, they are producers, and they actually act as producers, but they don't use the energy from the sun because they're so far down in the water that they don't get any sun. But that's the exception to the rule. So for our intents and purposes, almost all food chains start with a primary producer, and in most cases it is a plant. All right, so there's this concept of the 10% rule. The 10% rule is only 10% of the energy, and by energy what we're really talking about is calories. Only 10% of the calories, as a general rule, is transferred from one trophic level to the next. Think about that. That is incredibly inefficient. Being alive is incredibly inefficient when it comes to use of energy. The vast majority of the calories that you consume on a daily basis do not go towards keeping you alive or maintaining your health or driving chemical reactions. Most of that energy is actually wasted in the form of heat. Think about the engine of a car. We put gasoline in that engine, and that gasoline is converted into mechanical motion down the street. So we take the chemical energy in gasoline, we convert that into mechanical energy of the car, and that gets us to and fro where we want to go. But we know that engines in cars get incredibly hot. The internal combustion engine is not really super efficient. Well, being alive is way worse than like your worst internal combustion engine, especially for birds and mammals, because we're warm-blooded. We maintain a constant body temperature. The point is that from one level to the next, only 10% of the energy is transferred from one level to the next. Now, what does that mean? What does that look like graphically? I want you to make sure that you fill this in on your notes, because a portion of this is filled in, not a whole. Make sure you write in these numbers here. All right, so here are the producers. Why is this level bigger? This level is bigger because there are more individuals, more biomass, and literally more calories at this level. These are the organisms that eat the plants. They're called herbivores, right? These are our grass and plant-eating animals. 90% of the energy that is trapped in these producers does not transfer into the tissues here in these herbivores. Only 10%. Only 10% of the energy trapped in the chemical bonds here ends up as chemical bonds here. So much of that energy is used, or it's lost in the form of heat. So of all the calories that are here, only 10% transfer to this level. For the small carnivores, right, our second level consumers, our first predators. And then here is our third level of consumers, but it's our fourth trophic level, because here we have producers, first consumers, second consumers, third consumers. This is why the top level predators are so rare. Why is it that we see squirrels all over the place, but we don't see lots of wolverines or lots of top level predators? Why is it that the top level predators are so rare? I mean, that's one of the things that makes them so intriguing, is because they are so rare. We don't see them very often. Well, the reason they're rare is because there literally isn't enough calories at the top to support large numbers of those individuals, because so much of that energy is lost in the form of heat. Let's consider another graphic. Again, nothing to write here in your notes. In your notes, handouts, this is all right here, but let's just understand what this is showing us. Oh, let me back up. All right, so here's a certain level of corn, certain amount of corn that's got X number of calories in it. Let's call it 1,000 units of energy. So there's 1,000 units of energy in this corn and 1,000 units of energy in this corn. If we gave this corn directly to people, we would get this much energy. People could get this much energy out of eating this corn. But, because that's just one trophic level. Notice, 90% of the energy that's trapped in these tissues by photosynthesis from the sun, most of that is used or lost as heat. Only 10% ends up in the tissues of this individual. Well, let's say instead we don't want to eat just corn, but we want to have, the occasional cheeseburger. Well, if we take that corn and we give it to cows to raise cattle, only 10% of this energy in this corn transfers into energy in the cows. And then when we consume the cows, only 10% of this energy is available to us, because 90% of the energy that these cows consumed here, they use up or gets lost in the form of heat. Essentially what this is showing is that this amount of corn could potentially feed this many people, but that same amount of corn only feeds this many people, literally 10 times less. Right? This same amount of corn feeds a significantly smaller amount of people because we ran it through the cow and we ate it in the form of cheeseburgers and steaks as opposed to the form of corn. That's why, from a strictly ecological perspective, eating meat is not. It's a disaster from a strictly ecological perspective. Now, I'm not saying you need to be a vegetarian. I eat meat. There's plenty of reasons to eat meat. Variety to our diet gives us, iron and minerals and protein, etc. But my point is that from a strictly ecological perspective, from a conservation of energy perspective, eating meat is epically inefficient, because 90% of the calories that goes into that animal doesn't end up in us. It just gets wasted in the form of heat. It's just one more step in the chain, reducing the amount of calories that we could have. All right, let's draw this out graphically. What does this look like? All right, so you have this on your notes. I'm looking off to the side because you have this on your notes. So take a second and pause the video here and make sure you fill this in. But after you pause it, right, or before, right, listen to really this explanation. All right, so an ecological pyramid shows relative amounts of energy or matter contained within each trophic level. All right, so here's our first level consumers. Here's our first trophic level, our first level producers. Here's our primary producers, all the plants. All right, so plants are not 100% efficient. They don't turn all of the sunlight that shines on them and all of the water and all of the CO2 into glucose. But regardless of how many plants we have here, that energy is our starting point. So that energy is 100%. So 100% of our calories, say all the plants in a field, or all the plants, every single plant that's on your hunting land up north, for example, right? That's 100% of the energy. The first level consumers, right, the herbivores, they eat a bunch of that plants, a bunch of that energy, but only 10% of that energy is now in the tissues of those organisms. That's available to the next level. So the second level consumer is on the third trophic level, because of our first trophic level are the producers. So here's our plants, here's our herbivores, here's our first level consumers, our first predators. They eat these animals. Only 10% is left in that one. And then our top level predators eat these animals. So when we run it through all these food chains, 100% of the calories that is here, say 1,000 units of energy, gets reduced to 100 here, to 10 here and then only 1 here. This is why those top level predators are so rare. There simply isn't enough energy, right? You can never sustainably have more lions than zebras. Because if you have more lions than zebras, all those lions are going to eat those few zebras, and then that whole ecosystem is going to collapse. So this is why it's called a pyramid, of course, because with each successive level, it gets smaller and smaller and smaller. Now we really have 3 kinds of pyramids. We have 3 kinds of ecological pyramids. This one shows a pyramid of energy. We can also talk about it in terms of a pyramid of biomass, meaning if you could somehow magically weigh every single plant at your hunting land, that would be a huge number, and that would be our 100%. And then if you could take all the first level consumers, all the herbivores, and collect up every single one of them and put them on our giant scale, right? They would literally, in terms of their total mass, would be about 10% of this level. And then these second level consumers their mass would be about 10% of this. So it's a pyramid of energy. It gets smaller, and the amount of energy gets lower and lower going up each level. The sheer numbers get lower and lower, and the biomass gets lower. So not only do we have less mass going up with each successive level, we have literally less numbers, and most importantly, we have less energy. There's less energy at the top than there is at the levels below it. All right, so just take a minute and practice the 10% rule. If there are 1,000 units of energy available at the producer level of the primary energy pyramid, approximately how many units of energy are available to the third consumer? Interpret what is the original source of energy that flows through most ecosystems, and why must there be a continuous supply of energy in these ecosystems? And then third, infer why there are usually fewer organisms at the top levels of energy pyramids. All right, so go ahead and pause this video, answer these 3 questions, and then when you're done, unpause it. Okay, pause. All right, now we're back. Well, let's take a look at the answers. If there's 1,000 units of energy available at the producer level, the energy pyramid, approximately how many units of energy are available at the third consumer level? Right, so 1,000 units times 10% is 100 units. That's at the first consumer level. 100 units times 10 is 10 units. That's at the second consumer level. 10 units times 10% is 1 unit, so the third consumer level. Now, why do we do 3 calculations? Because it's the third consumer, but remember that first level are the plants. So we go plants, first consumer, second consumer, third consumer. So we're at the 4th trophic level, right? This first level consumer is at the second trophic level. The second level consumer is at the third trophic level, and so on. What's the original source of energy that flows through most ecosystems? It's the sun, solar energy. And why do we need this continuous supply? We need this continuous supply. Energy has to flow one way because so much of it is lost to the environment in the form of heat. It's either used up in driving the metabolism, the biochemistry of life, or it's lost in the form of heat. Why are there usually fewer organisms at the top levels of an energy pyramid? Because there literally is less energy there. There is less energy there. If our top level predators ate plants, there would be way more top level predators. But then again, they wouldn't be top level predators, would they? They would be lower level, first level consumers. All right, just about done here. Again, nothing to write here, but just consider the graphic. Pause it for a second and consider the graphic and listen to the explanation. Right? We know from photosynthesis and cellular respiration that consumers give off CO2 and producers give off oxygen. We haven't covered decomposition yet, but we know that decomposers can break down consumers. Decomposers give off CO2, producers give off oxygen. This bit here shows how matter gets recycled. We're going to get to that next. That's section 3.4. So here's our solar energy captured by the producers, and then we have the energy flowing through the consumers and through the decomposers. The matter gets cycled around. The carbons, the nitrogens, the oxygens, the periodic table of elements, the Legos of the universe. That stuff gets cycled around. Again, we'll get to that in section 3-4. But the energy flows one way, and much of it is lost in the form of heat. Last bit, again, nothing to write here, but just consider the graphic. Another analogy. The matter that makes up our body, that just gets cycled around, right? When I'm dead and gone, I'm in the ground, and I'm being consumed by the microbes and the worms and the detritivores, and my body's being broken down. That matter is literally going to get used up. It's going to get recycled. But the energy that's in me is only going to flow one way. That is not going to make its way back into the producers, which is where all the energy that's in me originally started. So energy flows one way over the wheel that gets cycled around. So here's the matter, and here's the energy. All right, just a quick recap. The major theme of this section is energy flows one way, matter gets recycled, and that flow of energy starts with producers and makes its way through each successive trophic level of consumers in our energy pyramid. The reason it's a pyramid is because 90% of the energy is lost going from one trophic level to the next. So we call that the 10% rule. Only 10% of the calories that are trapped in one trophic level ends up being trapped in the tissues of the trophic level above it. All right, so as always, supplement your understanding with the readings and with the YouTube clips on flow of energy. I hope that helped.